We finished the last class talking about some of the properties of electromagnetic radiation or light that are used to describe waves. The first and most important might be the wavelength, which has the symbol lambda. That's simply a distance in meters on the large scale or down to picometers, but it's the distance between two equivalent points on a wave, between crest to crest or trough to trough, what have you. The other important factor used to describe waves is frequency, or nu, lowercase Greek letter nu. And that's the number of waves that pass by a point per second. That has units of hertz, or waves per second, or cycles per second. I most commonly will write it as just per second, something like this. But in any event, those are the two. The third is a constant. The speed of light, or c, which is the c in Einstein's famous formula, E equals mc squared. That is always the same number, 3 times 10 to the 8th meters per second. So we can put these three things together and do a little bit of math. Let's take a look at these two pictures here first. I want you to ignore the one up on top, which just has a few definitions. Down at the bottom, we have two waves. One has half the wavelength of the other wave, 400 nanometers on the left, which is violet light. And the other is twice as long, 800 nanometers, which is infrared radiation. Now, remember from our study of the electromagnetic spectrum that short wavelengths have higher energy. So UV light and violet colored light might be around 400 nanometers, shown here. Much shorter waves, gamma rays and X-rays, are the very high energy waves, whereas long waves like radio waves and microwaves, and in the visible spectrum toward the red end, are much lower energy. We were dealing with a wave that was infrared, 800 nanometers, so it's just outside the visible range. So here again are our two waves. Now imagine they are going the same rate, same velocity, which is that constant c, 3 times 10 to the 8th meters per second. If they are going the same speed, which would have the higher frequency? In other words, which would have more waves per second going by a stationary point? And the answer, of course, is the shorter wavelength. So we have the beginnings of an inverse relationship here. The shorter the wavelength, the higher the frequency, and vice versa. And we can write that down if you like. That there is an inverse wavelength, inverse relationship. A small wavelength means a high frequency, and a high wavelength is a low frequency. So these things that have long wavelengths have low frequencies. These are the harmless wavelengths in the electromagnetic spectrum. The high frequency waves have very short wavelengths. So here's the inverse relationship that I've been talking about. C, the speed of light, is equal to lambda nu, or the wavelength times the frequency. So let's put this to work a little bit and do some math. So suppose I ask you, the red laser pointer I often use in class. On the back of any laser pointer, the FCC requires that you print the wavelength of the light. And the wavelength of light on my red laser pointer is 650 nanometers. Now remember that a nanometer is 10 to the negative 9th of a meter. That's shown right here, okay? So we can actually write this as 650 times 10 to the negative 9th meters, or in scientific notation, just make that 6.5 times 10 to the negative 7th meters. And the reason we want to translate to meters is because the speed of light is in meters per second, and so we want all of our units to line up. So in any event, let's do this math. So we have our formula, which is speed of light is equal to the wavelength times the frequency. We're solving for the frequency here, so let's just say the frequency is equal to the speed of light divided by the wavelength. And now we can plug these numbers in right here. We get the frequency is equal to 3 times 10 to the 8th meters per second divided by the wavelength, which is 6.5 times 10 to the negative 7th meters. And I want you to notice, of course, the units that are going to cross out. Meters cross out here, and you're going to be left with a unit of per second. Notice the numerator here, per second. So that's fine. That's cycles per second. That's hertz, and that is the units for frequency. And I don't have my calculator. I didn't do this, but you can see it's going to be a really big number because it's 10 to the 8th divided by 10 to the negative 7th. So we can expect an answer on the order of 10 to the 14th or 10 to the 15th or something like that. So the number of cycles per second that go by a stationary point is really high. Let's do another one. Of course, when you listen to snow closures, you listen to the news here in Washington, D.C., we listen to WTOP News. And WTOP is located at 103.5 on the radio dial. Well, guess what? That number has a meaning. 103.5 stands for 103.5 megahertz. And remember, a mega is 10 to the 6th. Okay, so this is really saying it's what this is 103.5 times 10 to the 6th, or times a million cycles per second. I'm going to write it like this, or hertz. It is a very long wavelength of light. So what is the wavelength? How long is it if we know that frequency? So once again, we're going to start with the speed of light is equal to the wavelength times the frequency. And again, we're solving for the frequency. I'm sorry, let's undo that. We're not solving for the frequency, we're solving for the wavelength. So the wavelength is equal to the speed of light divided by the frequency. Okay, so let's plug those numbers in. We know the speed of light is 3 times 10 to the 8th meters per second, and the frequency is 103.5 times 10 to the 6th cycles per second. You know what? We should convert this to standard scientific notation, which would be 1.035 times 10 to the 8th cycles per second. But nonetheless, when we do the math here, we see that the number is going to be pretty big. 3 times 10 to the 8th meters per second divided by, let's actually write it in there, divided by 1.035 times 10 to the 8th is going to be a pretty easy division. Divided by 1.035 times 10 to the 8th per second. And again, look at the units that cross out. Per second crosses out, and we get left with meters. And we want that because you want a wavelength. So this, and look at this, 10 to the 8th crosses out as well. So really the answer is 3 divided by 1.035. And I think, as I recall, it's about 2.9 meters. So let's take a look at the answers to our two calculations there. So we're saying a radio wave is about 2.9 meters long. And we go back to our little scale here, and look at that, radio waves. If we look up here, this is wavelength in meters, a wavelength in meters. And radio wave is about the scale of a human being, you know, a meter or 2 or 3. So we're right on. And the other one we did was looking at the frequency of red laser pointer light. So the frequency we guessed is going to be around 10 to the 14th or 10 to the 15th, because it's 10 to the 8th divided by 10 to the negative 7. And we go up here and we look at red light, and red light's going to be right over here. Here's our frequency. Look at that. It's between 10 to the 14th and 10 to the 15th. So we're right on. Our data says that's good. So we know a little bit about light and how it behaves as a wave, how it has a frequency and a wavelength, and these are things that are describable and observed. However, light does some other things. Light also behaves as a particle, and this is what's called the quantum concept of light. The quantum has a very specific meaning in science. It does not mean a quantum leap, meaning a big change. In fact, it means precisely the opposite. Quantum means the smallest possible energy change observed. So it's completely opposite from what you may understand. So we're going to give a little bit of history. A guy named Max Planck in the late 1800s observed that elements give off light when energized. And in fact, you already know this. The important thing about Planck's work was that it doesn't just give off any light. It gives off light when energized. Elements give off light only in very specific frequencies. And I want you to think about frequencies as colors from now on. And you guys know this already. I'm going to scroll down here and reveal this picture because of when you heat up a bar of iron, color does it glow? Of course, it glows this bright orange red. It doesn't glow green. It doesn't glow blue or purple or bright red or pink. It has a specific frequency that it gives off. The other great example is fireworks. Fireworks are made by adding certain elements. If you want a red firework, you give it strontium or lithium. If you want a greenish blue firework, you give it some copper, because those elements glow in specific frequencies. So this is Planck's work, that frequencies, remember colors, we're going to think of that as colors, are specific to elements. So again, if you want a bright yellow firework, you use sodium. You definitely don't use copper. So that was the first piece of evidence that something's going on that indicates that light acts at specific energies and not all possible energies. But then there are other things going on that are not explained by the wave model of light. So one of the big ones is called the photoelectric effect by Albert Einstein. It was his first Nobel Prize. At the time, he explained this, and it really revolutionized the idea of how matter, atoms, interact with photons, with light. So he noticed, well, he didn't notice, and many other previous scientists noticed that there is a thing that occurs when you shine a light of a certain frequency onto a metal surface. And what happens is that an electron gets knocked off from that metal surface. So here's kind of a cartoon version of this, that incoming beam of light will hit a metal surface and will knock an electron off. And therefore you can get an electric current by just by shining light of a specific frequency onto metal surfaces. This is the entire concept behind solar energy. Incoming light turns into a flow of electrons. So now you have an electric current. So there are some tricky things about it, however. That incoming light must have a minimum energy, a minimum frequency to knock an electron off. In other words, if it's not the right color, the right energy, remember color, energy, frequency, wavelength, all these things are interrelated. If it doesn't have that minimum energy, no electron gets knocked off, and it doesn't matter how bright the light is. So if your color light being shown on the metal is not the appropriate frequency, not the minimum frequency, that's like kind of like there's a threshold, then an electron does not get knocked off. So and you can crank up the brightness of that light, and it's still no electrons will get knocked off. Here's another sort of visualization of this. That here's some metal surface. It looks like it's potassium right here, and an incoming light will knock an electron off only if it is of a minimum energy. So remember, low energy radiation is red. The infrared and beyond, longer wavelengths, are low energy. And no electron is knocked off when red light is shined on this metal surface. But if you do have that minimum, so let's ramp up increase the frequency a little bit by having a shorter wavelength like green or blue, then an electron is knocked off. And it doesn't matter how bright you make this light. If it's a really bright beam of red light, no electrons will move. But even if it's a tiny, dull, very dim light of this green incoming light, I should show that in green, but you get the idea. Then an electron will move. And here's the interesting part. If you increase the brightness of the green light, it increases the number of electrons being knocked off, which indicates that light is actually a particle. That the brighter the light doesn't mean higher amplitude of the light wave. Instead, it means more particles of light, more pieces of light that are bashing into the surface and knocking an electron off. So back to this. The number of electrons, again, being knocked off doesn't depend on the brightness of a low energy wavelength. It depends on having the proper energy wavelength. And then the number of electrons being knocked off does depend on brightness. But again, it's about number of particles, which Einstein had a specific name for. All of a sudden, there is a new concept of light. And he made up a word called it a photon, a particle with no mass that carries a quantum of energy. And here's where quantum has a meaning. It has that minimum energy to knock an electron off the surface, okay? So light is now something that has a wavelength, has a frequency, is describable with wave-like properties, and yet can interact with matter. It has particle-like properties as well. So how do you think of this? It's a really curious concept, a particle of light that travels as a wave. This is not actually what light does, but it's the way I think of it. I think of it as a particle, like I've just drawn, that travels through space with a wavelength of some sort. And that wavelength is describable. So I don't know if this is what light actually does. I kind of doubt it, but I like to think of a photon as that way, a packet of energy, a particle that acts like a wave. So what is this quantum then? The quantum, again, is this minimum amount of energy gained or lost by an electron. And light emitted from an energized atom is quantized. It comes out in discrete amounts of energy. The reason we know that is because we only get one color of light that comes out of iron. That's not true. There's multiple colors, but they're very discrete. They're not a continuous rainbow of all energies depending on all the possible frequencies of light that are shined on it. It's just very specific energies. And again, that only occurs when that minimum amount of energy is available. Light given off by elements only occurs in certain wavelengths. The light given off by elements, the spectra of each element, is also quantized. Again, only certain wavelengths or colors. And those colors are characteristic of each element. So you can use the light given off by elements to identify elements. It is a characteristic property. Now, the wavelengths of light can be related to energy using a formula that we're going to look at right here. And it's E is equal to h nu. You're probably going to want to say hv. That's fine. But it's the energy of a single photon of light is relatable to its frequency through this thing right here, Planck's constant. Right there. And Planck's constant is an incredibly tiny number. It's 6.626 times 10 to the negative 34th joule seconds. That's an unusual set of units, but it's joules multiplied by seconds. You'll see why in a minute. And of course, nu is the frequency down here. So we can calculate the energy, the minimum energy needed to knock an electron off of a surface if we know the frequency of that light with which the metal surface interacts. So let's do a quick example of this calculation. By the way, Planck's constant is relatable to this minimum energy that is required to interact with an electron. Anything smaller than that will not interact with an electron. So here's an example. Remember, we did the red laser photon calculation where we calculated the frequency. And if you did that calculation, I know we didn't do it in this video, but we should have gotten an answer of 4.6 times 10 to the 14th hertz. So what is the energy of that red photon? Well, we just do E is equal to h times the frequency, okay? And remember, that's equal to 6.626, that's a 6.626 times 10 to the negative 34th joule seconds multiplied by the frequency. And the frequency is 4.6 times 10 to the 14th hertz, but we're going to write it as per second, cycles per second. And then recall, of course, that those units are going to cross out. This is in the denominator per second, so the seconds cross out, and you get left with joules. And you can see that this is going to be a really tiny number. I don't have my calculation in front of me, but if you do 6.6 times 10 to the negative 34th times 10 to the 14th, you're going to get an answer of, it looks like around 3 times 10 to the negative 20th, or sorry, negative 19th, roughly. So it's 10 to the negative 19th of a joule. If you don't know what a joule is, we can define that in class, but it's a unit of energy, a lot like the calorie. Okay, I think we've talked about the conversion between calories and joules leading up to this. So this makes sense. I'm going to write down an approximate number. What do we say? Approximately 3 times 10 to the negative 19th joules. That may or may not be right. I'm just doing this on the fly. But notice that's the energy of a single photon, and it is incredibly tiny, 10 to the negative 19th. So that kind of makes sense. Not going to be able to do a lot of work. One piece of light, one packet of energy. Here's another one right here. How about the energy of that WTOP photon? We know the frequency of that photon of light. It's 103.5 megahertz, which if we convert just to hertz, it's 1.035 times 10 to the 8th hertz. So same calculation. Let's take E is equal to Planck's constant times the frequency, where you get 6.626 times 10 to the negative 34th joule seconds, multiplied by the frequency, which is 1.035 times 10 to the 8th. I'm going to write it as per second this way so you can see better how the units cross out. And of course, numerator, denominator, we're left with a number of joules. This is so the answer looks like it's going to be approximately like 6.8 times 10 to the negative, what is that, 26 joules, very roughly. Now, what I want you to compare this to is here's a relatively high energy red laser light compared to a relatively low energy photon, which is a radio wave, 3 meters long. And notice the difference in energy. The red laser light has approximately 10 to the 7th, or 10 million times as much energy per photon versus the radio wave. Still tiny, but much, much greater than a low energy photon. All right, moving on. So what do I mean by the fact that elements have their own colors with which they shine? This is what's called the atomic emission spectrum. If you blast or energize an atom, that energy is absorbed by the electrons, not by the nucleus. And the electrons will revert back to a low energy state, and in doing so will give off some energy. And the energy they give off is a set of frequencies or colors emitted by atoms of that certain element. And what they look like is not continuous. They look like bright lines on a spectrum. Excuse me. So you don't see a continuous rainbow of all possible colors. You just see very few bright lines. It's quantized, once again, has specific energies, but it's not continuous. And again, every element has a very characteristic line spectrum. In other words, we can use, let me underline that, it's worth talking about. Remember, we've talked about a lot of characteristic properties in class: density, boiling point, melting point, things like that, that are specific to elements. The line spectrum is another one that can be used, the atomic emission spectrum. So every element has a unique, totally unique line spectrum, and that can be used to identify elements that are very far away. For example, we've never sent a spaceship even to our own star, the sun, never mind a star that's 4 light years or 100 light years or 30 million light years away. But we know what's in those stars. And the reason we know is because of the light that is given off by those stars. The way that light is analyzed is essentially it's broken up by a spectrum. When it's broken up by a spectrum, you will see individual bright lines, not what's shown here, which is a continuous spectrum. But the idea is the same. So let me show you what I mean. Here is the emission spectrum of hydrogen, the most common gas in the universe. And you notice when you break this up, and we will do this in class, when we break this up with a spectrum, you'll see, well, you'll definitely see 3 bright lights. You'll see the red, you'll see the greenish blue, and you'll see one of the 2 blues. On very rare occasion will we see this deep purple color, but it's there. But the emission spectrum from hydrogen gas looks something like this. So if you gather the light from a star using the Keck telescope, which I believe is in Hawaii, you can break up its spectrum into individual lines and see, oh, that star is relatively old. It's got only a little bit of hydrogen left. It's mostly helium. You got the idea. Here's one for sodium. we will see this one as well in class. And sodium, I want you to note, is bright yellow. There's not much going on in the visible spectrum except for a couple of really bright yellow lines. And once again, I want to flash back to this slide and remind you that if you want a yellow firework like that one right there, you use sodium because sodium glows yellow in the visible spectrum. Okay. Whoops, I'm going too far. Let me back up. Sorry. Here we are. Another example, and you can look these up. There's hydrogen again. So same idea. We see 4 bright lines at characteristic frequencies. This has a piece of history that goes along with the history of chemistry in particular, is a discovery of helium. Now, helium's a noble gas, not very reactive, so it's actually difficult to detect, and it's not very common in our atmosphere. It was discovered first because an astronomer in the I want to say the 1860s, whose name I've forgotten, was looking at the light given off by the sun. Now, it's been known since the time of Isaac Newton that stars, light could be broken up into its spectrum, and stars do that as well. When the light from the sun was looked at, something very different was visualized that had not been seen before. In particular, here's helium, called helium now. In particular is this bright yellow line. Very different from hydrogen. The other stuff, yeah, there's some blues and greens, there's a red stripe, but look at this. So this was something that had not been seen on Earth as of yet, and there were many elements that had been identified based on their spectrum first on Earth, but this one had never been identified. So the discoverer of this, and again, I've forgotten the astronomer's name, named it helium. Must be a new element. It's got a totally unique spectrum. Nothing else has this series of blue light and this bright yellow thing in the middle. He named it helium after the sun, Helios. And it wasn't until about 30 years later, in the late 1800s, when another scientist who I can't pull off the top of my head was doing work with uranium. Uranium, of course, decays via alpha emission. Remember, alpha is a helium nucleus. And if you give it a little time to interact with a couple of electrons, it's going to steal those electrons and form the gas helium. So he collected the gas helium, he analyzed its visual spectrum, and lo and behold, and again, he didn't know it was helium at the time. He was collecting this thing that was off-gassing from uranium. And lo and behold, he saw that bright yellow stripe, and helium for the first time was isolated and purified on Earth. So again, the visual spectrum are characteristic properties of elements. So where does this spectrum come from? Well, it comes from electrons, as you've probably already guessed. And you need to know a little bit how electrons behave. So electrons, when they are not energized, live, and I don't like the word live, electrons are not alive, but nonetheless, let's use that. They live in what's called a ground state. And a ground state is the lowest possible energy state of electrons. Remember, I've stressed this many times. Nature likes a low energy state, and it will do what it can to stay in a low energy state. So the ground state is the most common electron configuration in an atom. And it's very stable, non-reactive at that point. Well, I wouldn't say non-reactive, but still, it's stable. But when atoms absorb energy, and it can be all kinds of different energy. You can heat it up and glow iron, for example. You can blast it with electricity. There's a neon light for you. Or you can even shine light on it of the proper frequency. Atoms will absorb that energy, but it's not the nucleus. It's the electrons. And the electrons will jump to a higher energy level. And that's the technical term for that is electron is promoted to a higher energy level. But that's unstable. It will not and cannot stay there for long. And so it'll revert back to the ground state. But when it does that, it has to release the energy it originally absorbed. And guess how it does that? When it reverts back to the ground state, it releases the energy in the form of light, a photon. And again, each element has a specific set of wavelengths, and there are a number of different promotions that can occur. There are a number of different relaxations, that's called, to a lower energy state. So there's a number of different stripes or bright spots on a spectrum, but it's not continuous. It's discrete. So let's look at a couple of sort of visualizations of this. So let's say we have a photon in the ground state. He lives down here. And that photon is energized, again, by electricity or by shining a light on it, whatever it might be. That photon can be promoted to a higher energy level and live up there for a little while. Okay, just showing it over here. But again, that is not stable, and it will jump back down or relax back down to the ground state. And when it does, it's got to release that energy. And when it does, it releases a photon. Okay, so how come is it again that, oh, again, and let me show you another thing. And the energy is quantized. There are certain steps, certain energy levels in an atom, and there are no between steps. So I want you to visualize this as you going up a flight of stairs to your next class. You cannot take a half a step and hang out in between steps. That doesn't exist. That is a state that does not exist when you climb those stairs. Instead, you must take quantized, oops, I didn't mean to do that. You must take quantized steps of certain energy changes to get up the stairwell. Electrons do the same thing. And therefore, if you were an electron and you were to, you'd say you were up at this energy level here, you cannot release this photon, the amount of energy change to that right there. You can't release this photon, the energy change there. You can't release every possible photon in distance on the way down. It's not like this scenario where there's every possible energy change available as an electron slides down a slope. Nope, that's not what happens. There are only discrete, or again, quantized available energy changes. So take a look at, here's an example of hydrogen, for example. Let me slide back down here. Hydrogen, let's get an electron. Hydrogen starts with an electron in a ground state, and depending on the incoming energy, that's going to, you know what, we should draw that down with the photon. Depending on the incoming energy that's going to hit that photon, there can be multiple different promotions. That electron, you know, could be promoted just to the first energy level, or to the second, or to the third, or to the fourth. Sorry, this is the first energy level, the ground state. So this would be the second, the third, the fourth, etc. And you can see there are multiple possible relaxations as well. You could go from the fourth energy level all the way back down to the first, or from the third to the first, which isn't shown, or from the fourth to the second, sorry, that's the fifth to the second. And therefore, each one of these gives off a different colored photon. And so you might get different color stripes depending on the energy change in that electron. So hydrogen, remember we looked at hydrogen, let me scroll back up, and we saw hydrogen has these discrete bright stripes, okay, a red right here, a greenish blue, and then two dark violets. And that's because hydrogen does this right here. Hydrogen, these are the four stripes you'll see in the visible spectrum. It's called the Bohr series, and you can see the relaxation energies right here. There are multiple possible ones. There are some that we can't see. In fact, there's a whole series of ultraviolet energy changes. You can see those are the really high energy relaxations right there. And remember, ultraviolet is the shorter wavelength, the higher frequency, higher energy. There are also lower energy relaxations, and that's shown here. And those are in the infrared, which are lower energy than the visible spectrum. And so you've got some low energy electron relaxations here. So this is, I've skipped ahead a little bit, but this is the Bohr model of the atom. Niels Bohr in the early 1900s based his work on explaining this line spectrum of light. He based it on the hydrogen atom. But why would you do that? Why would you base it on the hydrogen atom? Simplest possible case, right? One proton, one electron, and that's it. And he coined these terms, the ground state and the excited state for the electrons. And he said, and confirming Einstein's work from the photoelectric effect and Planck's observations of specific colors associated with elements, he said there are only a certain number of allowable energies for an electron relaxation, no in-betweens. So once again, there are only certain allowable energy changes for an electron. Oh, you know what? I shouldn't draw it like that. Let's draw it like this. Let's start an electron on this stair. He can go to that stair, or you can go down to that stair, but there's no in between. There's no in between changes. You get the idea. Okay, back to the Bohr model. He called these energy levels orbits, and we're going to find in a future class that electrons do not orbit like planets around the sun. It's a three-dimensional system, not a flat plane. Okay, and they're not spheres either. They're not layers of an onion. It's a good visual model, but that's not what they do. But he used this again as an analogy. He called them orbits. Bigger orbits further outside the nucleus have higher energies, and smaller orbits have lower energies. And he assigned what's called a quantum number to each orbit. And he gave that quantum number a symbol, n, and called them n equals 1, n equals 2. These are the things called energy levels. So the innermost level, n equals 1, is the lowest energy level. N equals 2, n equals 3. These are called quantum numbers. First quantum number, second quantum number, etc. Okay? Back to this. Okay? And the beautiful thing about Niels Bohr, his work, was that it described the emission spectra of hydrogen perfectly. Again, this is all mathematical work that he calculated the energy changes of the electrons and then changed those energies to frequencies or colors of light using the E equals hv Planck's constant equation that we just did. And he was able to predict using those mathematics, these spectra from hydrogen. This is, by the way, hydrogen's spectrum, perfectly. So it was a huge success in the very beginning of the quantum description of atoms. He won a Nobel Prize for this work. He had a long career as kind of the grandfather of the quantum theories of the electron behavior. This is his only Nobel Prize, though, but he is probably more influential and important, right up there with Einstein and Schrodinger and some of these people you've heard of. The problem with Niels Bohr's work was this. He predicted hydrogen's emission spectrum perfect, but it didn't work for any other element. He could not predict the emission wavelengths, the colors in an emission spectrum for any other element other than hydrogen. And I think the answer should be obvious because it's complicated. You have more than one electron. And so on that note, we'll close here. And thank you for paying attention. I'll see you shortly.